In traditional Android UI development, building a screen meant wrestling with imperative logic. You had to manually inflate XML files, hook up elements using findViewById, and write verbose code just to mutate a view's state on the screen. Jetpack Compose replaces that brittle workflow with a declarative paradigm, dependencies. This works through a process called recomposition. You can think of the UI as a direct mathematical output of your state data. Whenever that underlying data changes, the framework automatically redraws the affected components to match the new reality. To master Compose, you have to abandon the habit of manually updating visual elements. The focus shifts entirely to designing a clean architecture of state variables and the interactive callbacks that trigger them. The foundation of this system is the app-composable annotation. When you add this to a standard Kotlin function, it acts as a compiler plugin that transforms your code into an actual UI element on the screen. Looking at this code editor, the setContent block inside the main activity is the origin point. Inside, we call primitive composables, like this text function. Directly above that, the @preview annotation lets you see the result immediately in Android Studio, saving you from running full builds. There is a strict rule to keep in mind. Functions marked with @preview cannot accept any parameters. If a component requires external data to render, you have to create a dedicated, parameter-free wrapper function to feed it placeholder data for the preview window. Text labels are static primitives. To build interaction, we introduce components like the button composable. A compose button does not contain any internal logic determining what happens when it is pressed. Instead, it relies on an onClick parameter. You pass a Lambda function into this parameter, and the system executes that specific code when the user interacts with the button. Out of the box, the Compose UI library gives you the complete material design visual hierarchy. Depending on the importance of the action, you can call specific composables for the solid filled button, the shaded tonal button, the shadowed elevated button, the bordered outlined button, or low-emphasis text buttons. The core mechanic is identical across all of them. Even for the simplest user interaction, you are passing an executable function downwards into the component so that it can report the user's action back upwards. That upward reporting mechanism is how we handle user input. To see how components manage changing conditions over time, we use binary interactive components, like the switch. A switch needs to know if it is currently on or off. We store that condition using the mutableStateOf function. By wrapping that inside a remember block, we ensure the framework retains that specific value in memory, even as the UI rapidly redraws itself. We pass that stored value directly into the switch's checked parameter. This is how the component knows its current visual status. When a user drags or taps the switch, the component cannot flip itself. It fires the onCheckedChange Lambda callback to request a state update. This creates a strict unidirectional data flow. This visual shows the two fixed outputs of this cycle. If the state variable is false, the switch renders as an unchecked gray track. If the variable updates to true, recomposition fires and it immediately redraws as a checked purple switch. We can examine the checkbox composable to see how heavily standardized this pattern is across different components. Looking directly at the checkbox code implementation, it uses the exact same checked parameter to receive its state, and the exact same onCheckedChange Lambda to overwrite that variable when tapped. Checkboxes do offer a third indeterminate state, rendered as a single dash, to handle complex partial selections across multiple nested options, expanding beyond simple true or false logic. But the primary rule of the Compose architecture holds firm. State data flows down into the composable, and user events flow up through Lambdas. When you need group logic, like a list where only a single item can be selected at a time, you use an array of radio buttons. To construct a functional radio button, you pair the circular primitive with a text label. Because you want these to behave as a single clickable target, you nest both elements together inside a row component. You then wrap the entire list of rows in a parent layout column and apply a Modifier.selectableGrouping. This explicitly informs screen readers that the nested items share a single context, ensuring correct accessibility behavior. We can take that concept of state-driven layouts further. Instead of just changing a button's color, a simple Boolean state can dictate whether an entirely separate UI surface is visible or hidden. This basic drop-down menu relies on an expanded Boolean state to control its visibility, and an onDismiss request handler to close itself if the user taps outside the menu area. The trigger mechanism is usually an independent icon button. Tapping that icon flips the expanded state to true. Because the layout is a direct function of that state, the framework immediately renders the drop-down menu container and populates it with nested drop-down menu item composables. Scaling this interface up involves layering more primitives into the list. You inject horizontal divider elements between sections, or add leading and trailing icons to the individual items. Looking at this complete drop-down implementation, the dividers cleanly separate the profile settings from the support links, while the nested icons provide immediate context. Complex Android interfaces are simply hierarchies of these primitive functions, seamlessly layered together and controlled by localized state variables. Up to this point, we've only handled discrete Boolean logic, but interfaces also need to map continuous data streams, like adjusting the volume or setting a custom brightness level. For these tasks, we use the slider. Looking at its anatomy, it consists of a draggable thumb for selecting a value, a horizontal track representing the full range, and optional tick marks. Because a slider lands on fractions of a whole number, it cannot use a simple true or false state. Instead, we initialize it using mutableFloatStateOf to handle decimal positions. The core parameters stay exactly the same. You pass the continuous numerical position down via the value parameter, and you catch the continuous drag events flowing up using the onValueChain lambda. You can force this continuous stream back into discrete intervals. By defining a custom value range and assigning a specific number of steps, the thumb will automatically snap to predefined notches along the track. Compose also provides a dedicated range slider variant. This captures an array of 2 floats, allowing the user to set specific minimum and maximum boundaries, like filtering the price range. Whether the user taps a button or continuously drags a slider across 100 data points, Compose handles the underlying data synchronization identically. Visually comparing the checkbox, the drop-down menu, and the slider proves the consistency of this framework. Despite radically different visual outputs, they share the exact same architectural skeleton: a parameter to read state and a lambda callback to write state. The visual UI is completely decoupled from the logic. Composable functions are intentionally dumb. They do not store their own data, and they never manually mutate their own appearance. A composable's only job is to report user interactions to a state variable. The heavy lifting of tearing down and redrawing the pixels on the screen is handled entirely by the Compose framework. By adopting Jetpack Compose, developers gain a highly predictable, modular, and unified API surface that eliminates the boilerplate of legacy Android UI development.